Okay, well, welcome everybody. This is a packed house. I don't think I've seen this place this full before, so this is pretty amazing. This is our second deep talks of the season. Sanford Lab puts these on every second Thursday of the month through May. So next month is our Nobel Day celebration, so I hope you can make it for that. That's actually going to be on the 13th, so that's a Friday, I believe, instead of Thursday. I think that's right. So I need to thank a few people before we get started today. Crow Peak Brewing, of course, who sponsors this event from the beginning. Free beer is courtesy of them, so if we can give them a round of applause. And then, of course, the Sanford Lab Homestake Visitor Center for providing us this space. And tonight's food was brought to you by the Northern Hills Federal Credit Union. And so I think most of you are familiar with the story of our facility. What was once a gold mine has been reclaimed and transformed into America's world-class underground laboratory, the Sanford Lab. Tonight's speaker has been closely involved with one of the most challenging and vital pieces of the transition. As a consultant, he led an original feasibility study at the facility, examining the possibility of converting it into an underground science lab. Now, he will soon see the Ross Shaft Rehabilitation Project through to its completion. He is the far site conventional facilities engineer for building and site infrastructure, right? Working on the Fermilab-managed long baseline Neutrino facility at the Sanford Lab. And tonight, he will help us celebrate over 80 years of the Yates and Ross Shaft. Please help me welcome Syd DeVries.
All right, can everybody hear me? Yes. Awesome. Thanks very much, Matt. Well, it is really nice to see the turnout that we have tonight. It's really exciting to see that there's a lot of interest in this subject, and I appreciate everyone coming out. In September of 2003, I was working for Dynatech Mining and sitting in my office in Richmond Hill, Ontario. My boss walked into my office, and he dropped this pre-feasibility study on my desk, and he said, "Read this." He says, "I want you to look after this project here." And it was a pre-feasibility study looking at taking the old Homestake mine and developing it into an underground science laboratory. I remember it very clearly, but little did I know that 16 years later, I'd be standing up here and talking to you all about everything that has led up to this particular time here. It's pretty amazing to look back and see that one particular event and where it's led to me today. So, anyways, let's get started with the talk. So I'm going to talk to you about the Ross and the Yates shafts, from Homestake to the Sanford Lab and beyond. So this is basically a synopsis of the past, present, and future of the shafts at the former gold mine and current lab. So just a little introduction. So the Yates and the Ross shafts are the means of entry into the facility. They're the means of access that are provided in this, this graphic here is a nice representation that shows where the Yates and the Ross shafts fit relative to the 4850 level and a lot of the experiments that are either under construction or being built. And it basically shows how important those shafts are. They are the way to get down to where the science is happening. So the Yates shaft has been in service for 80 years, and the Ross shaft has been in service for 85 years. So both originally were constructed to provide access to an ore body that continued to get deeper and could no longer be accessed with the older shafts. And those older shafts were the Ellison and the B&M shafts. So another important feature and function of the Yates and the Ross shafts is that they're not only do they provide access to the facility, but they're the conduits by which the fresh air enters the mine, the lab. So on this representation, you can see the long section of the old Homestake mine workings and where the Yates and the Ross shafts fit here. And the blue color and blue arrows represent the fresh air that goes into the facility. So this demonstrates that this is also an important feature. This is what makes the Yates and the Ross shaft very important to the operation of the facility. So we're going to talk a little bit first about the Yates shaft. So the Yates shaft was constructed for two primary reasons. It was constructed after the Ross shaft was done, and it was well known that the Ross shaft would not be able to keep up with the production demands for the Homestake mine. In addition to that, the Ellison shaft was reaching the end of its life, and it needed to be replaced. So construction began back in 1938 and was completed in 1941. The shaft was named after one of the general managers for the Homestake mine, a guy by the name of Bruce Yates. Not unlike a lot of other shafts, it was constructed in phases. First phase got it down to 4100 level, and eventually it was deep into the 4850 level in 1954. And the type of construction that was used for the Yates shaft involved what is called a pilot and slash method. What this basically means is that raises were driven from the bottom level all the way up to the very top, which creates a pilot hole. And how that's advantageous is that it enables the excavation to be done from the top down, and the blasting is basically done into the pilot hole. The muck falls to the bottom, and it speeds up the whole process of shaft sinking. Normal shaft sinking in a greenfield operation basically does the excavation from the top down, but all the muck has to come from the bottom up, and it interferes with that cycle. So that's one of the reasons why the Yates shaft was able to be sunk and constructed in the short period of time, which essentially was 3 years. The type of construction there are steel members that are part of the first 300 feet, and the rest of the shaft is constructed out of timber. So this isometric view basically shows you the timber structure which makes up the compartments in the shaft. So basically during mining operations, the shaft provided access for the miners, materials and equipment, and as well as provided hoisting capability for the ore and waste that was being mined. And the spacing of the sets was every 6 feet. And one of the interesting features, I think, was the fact that it was made out of timber wasn't because they really preferred to make it out of timber. It was because the steel was not available, was not readily available at the time, because the Second World War was basically just getting started. So this is a plan view of a typical shaft set for the Yates shaft. The dimensions are 27 feet 8 inches in this long section and 15 feet in width. And it shows you the various compartments. There are 2 cage compartments where the cage conveyances ride up and down. There are 2 skip compartments. And then there's basically compartments here that provide, that basically support utilities. So over the last few years, and basically starting back in 2008, it was when re-entry was established to develop the Sanford Lab, the timber furnishings needed to be refurbished. So a maintenance program was started, which basically utilized these unique kind of conveyances for performing the maintenance work. So these 2 figures right over here show special work decks that were used in the skip compartment. You can see that underneath these conveyances are these skips, which are the conveyances which raise and lower, which bring the waste rock out of the mine. But they basically retrofitted them with platforms on top, so the guys could stand on top and do their work. And then in the cage compartment, a special conveyance was built to provide the platforms for the guys to work off of. I'm not going to bore you with these numbers here, but basically this kind of And if anybody's interested in a lot of the data in terms of the dimensions, the speeds of the conveyances, they can talk to me about this afterwards. But, generally speaking, you're dealing, I think what's of interest was that the hoist operating speeds, back in the past were anywhere, the cage would and the skips would operate between 1,300 and 2,500 feet per minute. But now, during this heavy maintenance cycle, the speed of those conveyances has been reduced to 500 to 800 feet per minute. So just to show you a few of the steps that are involved with the work that's going on in the Yates shaft with this, what we call top-down maintenance. So the way things work is the crews go down and they first of all remove the lacing. And lacing is basically a series of planks that are installed vertically around the perimeter of the shaft. And that lacing would provide basically support for the timber sets, but it would also provide a ground support for the rock behind it. Anyways, over time, a lot of the rock has dislodged there and loosened up. So part of this top-down maintenance involves removing the old lacing, and this figure here shows that the old lacing and some of the other rotten timber gets dumped into the skip, and it's brought up to the collar and basically dumped in this place over here, where it's then picked up and disposed of. And then after, once the lacing has been removed, then the guys come in and they install rock bolts and mesh to secure the ground, and then the timber lacing is put back in place, and other reinforcement of the timber is provided as well too. And obviously, one of the most important components of a shaft is the cage conveyance, and what these photographs basically show are is a new cage that's being installed in the shaft. So I want to say it was probably about 2010 when a new cage was built. And basically, for those of you who haven't been underground before, a cage is basically a container that is used as raised and lowered up and down the shaft, which brings man, material, and equipment underground. So the next graphic, well, this one basically shows the hoists. We've got these are 25-foot diameter hoists. One is for the one's called the production hoist, which runs the skips. The other one is called the cage hoist. This one here is the production hoist, which runs the skips, and this one here is the cage hoist. And as you can see, what I think is really interesting is, these hoists were installed in the late 1930s, early 1940s, and they're in fabulous shape. They're extremely well maintained, and there's a lot of credit that has to go to the maintenance crew for that. So now the Sanford Lab is no longer a mine. So what do these conveyances, what do they need to do? The big thing that they need to do right now, and specifically the Yates shaft, it has to support science. So what you see here are a couple of really important packages which are being delivered. The Lux experiment, a number of years ago when it was built, was basically launched. It was able to fit into the cage. As you can see, everything's wrapped up real nice. It's going into the cage at the collar. And then it comes out at the 4850 level. So basically, the Yates shaft provides a real important function in terms of being able to support science, bringing important science equipment underground. So this next video I have is of the delivery of the LZ experimental equipment. And this was taken, I want to say, maybe 3 or 4 weeks ago. An important step in with an experiment that's specifically designed to search for dark matter. So we'll just run this through.
How do you get a 5,000-pound, 9-foot-tall dark matter detector nearly a mile underground? Very carefully. In Sanford Underground Research Facility's surface cleanroom, the Lux-Zeppelin collaboration spent months assembling LZ's inner detector. In October, it was ready for transport to the underground. This high-stakes move was meticulously planned and practiced. It It required transporting the detector from the clean room to the Yates head frame, down a mile-deep shaft and through a narrow drift on the 4850 level, all without damaging or dirtying the detector. To keep LZ well sealed from any contaminants during its journey, the detector was triple wrapped in protective plastic and secured in a frame for transport. A forklift slowly carried the detector to the Yates head frame. There, engineers carefully attached the frame to the underside of the cage with slings and straps. The detector narrowly fit in the elevator shaft. A trip that normally lasts 12 minutes took over an hour as the crew slowly moves the detector nearly a mile underground. Once detached from the cage on the 4850 level, the detector was moved through the drift using air skates on a temporarily assembled surface. That evening, LZ collaboration members around the world received news that the move was successful. Now the detector must be installed in the Davis Cavern water tank. There, in 2020, LZ will begin its search for dark matter.
So that was just hot off the press. So this slide basically shows what does it look like at the 4850 level. We already saw that with that previous video. And I'd like to show this to compare what does it look like at some of these other mining levels. Most of us who work at the lab basically go down to the 4850 level and everything's nicely lit up. We've got walls that are painted white, and it really looks like a really, it almost has an office feel to it. The rest of the levels don't have that look at all, as you can see. All right, so what about the future of the H shaft? Essentially, the H shaft is integral to the future of the Sanford Lab. Timber shafts, the timber sets in the shaft are not a long-term solution. Currently, the shaft is available only 40 hours per week to support science. And the rest of the time is taken up with shaft maintenance. So that's a lot of time that is not available to be used for access purposes. So the SDSTA is currently investigating potential shaft refurbishment options. The final solution will depend on requirements, costs, construction schedule, and available funding. So all I can say is stay tuned, and we'll see what comes out of that. So now let's transition over to the Ross shaft. The Ross shaft is the one that I spent the most time on, so I have a pretty solid understanding of what we've got going on there. So the history, just to give you an idea, approval was provided to construct the new shaft back in October of 1932, and the shaft would be put into operation basically 26 months later, which is just over 2 years. I find that just amazing. I mean, if you consider that we've been working in the Ross shaft doing the refurbishment for over 7 years now, and we're just finishing up, what those guys were able to do back in the day is very impressive. So the shaft is named after one of the mine superintendents, A.J. Ross, and that's a picture of the guy right there. It too was developed in phases. It was originally sunk to the 3950 level, eventually deepened to the 5000 level, and that's where it's at right now. It also utilized a pilot slash method to perform the excavation, similar to what I described earlier. Similar to the Yates shaft, it provided access for the miners, materials, and equipment, as well as ore and waste hoisting, ventilation, and pathway for utilities. But one of the unique aspects of the Ross shaft is it's the main pathway for the dewatering system, and still is today. All the facility water that collects is pumped up the Ross shaft and then eventually goes to the wastewater treatment. Now, one of the differences with between the Yates shaft and the Ross shaft is that it's constructed with steel sets. So big difference, steel versus timber. And really what that was because this construction was done before the Second World War, so steel was readily available. So I got a few photos here that basically show the development of the initial construction of the Ross shaft, and this is basically what the site looked like as they're just starting, developing the shaft. And what I find really, basically you've got, a shack here, which is, providing access, because there's a pilot raise that goes all the way down. So this is kind of like a mini head frame. But what's striking to me in this photograph is you got a couple of gals who are walking here in dresses, okay? Certainly personal protective equipment was not considered at that time. Either that or security wasn't too strong either at that time. So now the site is being developed. You can see more construction going on. There's the mini head frame that I was talking about before. And so now they're starting to open up the foundation for the construction of the crushers. And you can see all the lay down for all the steel. That was part of that construction. And now this is a nice photo of the crusher, the big building where all the crushing of the material was done. And the next photograph, now you can see the head frame really taking shape, and with the metal cladding being installed, and and once again you've got the crusher room is really taking shape too. Notice something here. December 31st, 1933. Perhaps there was some early global warming going on at that time here. Love some of those cars there too. It's almost like Al Capone must have gone up there for a visit. So here we see the hoist being installed in the hoist room. It's very impressive to see these large drums, and yeah, it's really impressive construction going on here. All right, so now let's fast forward, and the Ross shaft has been used for about 70 years. But let's keep in mind though that most shafts are built to last about 50 years. Okay, so even pushing it to 70 years was really kind of stretching its overall duration of service. But after 70 years, Homestake was shut down and the Ross shaft was buttoned up. And in 2007, the decision was made to convert the underground mine into an underground laboratory. So now the Ross shaft would need to be important to part of the future of the Sanford Lab. So when we look at doing a refurbishment of the Ross shaft, we've got to first of all start asking some important questions like what are the requirements for developing and maintaining a lab underground. So what does it need to do? Again, provide access for men, equipment, and materials down to the 4850 level. This shaft is going to have to provide waste rock hoisting. We're not hoisting waste rock right now, and we're getting, there's a lot of work that's being included in that refurbishment that will re-engage that waste rock hoisting capability. It has to provide emergency egress, and it has to provide long-term service. We're talking 30 to 50 years. Again, it needs to provide a conduit for ventilation, and we got to put a lot of utilities down. We've got normal power, we've got industrial and fire water supply. The discharge water system has to go up the shaft. Communications, compressed air, and cryogen piping for experiments. And I'm going to have a slide a little bit later on that's going to show a little more detail on that. So what was the condition of the existing steel before we got started? You might notice that this webbing over here has got a bit of daylight showing through it, okay? I wouldn't call that really, strong from a structural perspective here. A lot of the steel we took out looked like that, okay? So it badly needed to be changed. And the fact was, like I said before, most shafts, if you get 50 years out of them, you're doing good. And, they pushed it all the way to 70 years. Essentially, the Ross shaft could not serve the access needs for surf in this condition. So we're talking extreme makeover here. All right, so a new design would have to be completed to replace the existing steel furnishings. So here you have a photograph of the original design, a couple of steel sets with a 6-foot spacing in between, basically built in the yard right around the head frame. And And this is what the new shaft steel looks like. And you can see that there's quite a bit of a span difference here in the vertical direction, whereas this is a 6-foot span over here. This is an 18-foot span. But I think, what I find interesting with this photograph too was they kind of had the same idea as we did. Let's build a couple of sets in the yard just to see how they all fit together, get all the guys who are going to be putting them, that are going to be installing them, and see if there's, if there's any changes that need to be made. They had the same idea in the old day. Do a pre-assembly. Make sure everything fits together. Because if everything fits together here, it's going to fit together underground. And there were a total of 850 of these that had to be installed in the Ross shaft. So the refurbishment work involves building new work decks, basically taking out the old cage, which is now parked in the visitor center here, and replacing it with special conveyances that provide access for the guys to do the work. So this is just a kind of a graphic showing the new steel sets in the shaft with the work decks suspended in there. So what are the steps that are involved with refurbishing the shaft? First, you go in and you cut out the steel. So you got guys with torches, and piece by piece, they're removing the old steel. That steel gets dumped into one of the conveyances. We have one of the skips is still in place in the Ross shaft, and basically they would dump the waste steel in that conveyance, be hoisted to surface, and then dumped into these bins that you can see right over here, and then shipped off to recycle. After all the steel is removed, ground support is installed. So you see a nice picture here where Jerry Hinker and James Gregory are installing ground support in the shaft, working off those platforms that I was describing earlier in that previous slide. Then comes time to install the new steel. So all the pieces are lowered with those conveyances, and piece by piece they are installed. And this is kind of like a bird's eye view of steel installation that's going on at what we call a bearing set. So bearing sets are basically installed at every 10 sets, or about 180 feet, and they are the load bearing sets. Okay, you can't just start from the top and then hang all the steel sets and expect it to be able to support that load. So you got to break it up into intervals. So these bearing sets are basically anchored to the wall and basically support every a series of 9 sets below it. So basically the procedure is you once all the ground support is installed, then you hang these what are called studdles from the set above, and then you basically install the perimeter steel around it. And then once the perimeter steel is in place, then you put all the steel in between. Now, as part of these bearing sets, the installation of these bearing sets, you've got what we call these that are called saddles, and that essentially these are special welded components that are anchored into the rock wall. There's a number of rock anchors that are drilled into there. So every one of these bearing sets has 6 of these, we call them saddles. And that's what bears the weight of all the steel that's in the shaft. So one of the challenges that we had in the Ross shaft was in the section of the shaft that's called the Ross pillar. And the Ross pillar is right around, it covers about 1,000 vertical feet in the shaft. And that section of the shaft actually went through part of the ore zone, okay? And that ore zone was under a fair amount of stress. And what happens over time is that if you create an opening in a section of highly stressed ground, it tends to want to squeeze over time. Now, the problem was once you've made a commitment to sink a shaft and you encounter highly stressed ground, it's not like you're going to stop it. You're just going to keep on going through and try to deal with it over time. So what I wanted to show you here was, that by the time we got into the shaft refurbishment, the Ross pillar, the amount of ground movement that had taken place had shifted the existing steel in this particular direction, starting this way and going into this way, and had made a kind of a wow in the shaft. shifting the shaft steel by as much as 6 inches. Now you can imagine trying to run the conveyances up and down through the shaft, and they're kind of going through there and weaving in and out. Especially if the steel is squeezing, the conveyances can get stuck through there. So one of our big challenges as part of this project was to fix that problem. But that was a significant challenge. What you see in this slide here is an outline of the survey of the rock wall, okay, at one particular location in the shaft. And you can see here, this is where we needed to put the steel set in order for it to be straight. Well, we've got rock in the way here, and that rock has basically encroached over time because of the squeezing that has taken place within that Ross pillar. So one of our big challenges was, well, we've got to mine that out, but we can't drill and blast it, which would be the most efficient way of doing it, because we have to maintain access through the shaft as it's being refurbished. We've got utilities that are running through the shaft. It needs to continue to serve its purpose as an emergency egress. We got to figure out a way to deal with this here without interfering with those other functions. Well, basically what that means is we're going to have to employ non-explosive excavation techniques. And what you see with this fellow over here, he's basically using a rock saw and cutting into the rock. And with using a tool like this here and chipping hammers, we managed, through the work what those guys were able to do, is to remove the rock that was in the way and able to move the shaft steel back 6 inches and to bring it back into its vertical position. That was a very difficult task. All right, so let's take a bird's eye view of the Ross shaft as we're looking down. So we're standing in this particular slide. We're standing in the cage compartment over here. You've got the south skip, which runs in this compartment over here, the north skip. So these are the rock boxes that run up and down the shaft. There's the counterweight compartment. Just so that you know, you need to have a counterweight that runs counterbalance with the cage conveyance. Otherwise, that makes it much more efficient from a hoisting perspective. It balances the loads a little bit more. Now, the skip doesn't need a counterbalance because one skip counterbalances the other. And then in this northwest corner, you've got a section which is called the manway compartment. Even though it's not shown in here, there are ladders and platforms in here to provide emergency egress for folks as well, too. And then in that far northwest corner, you can see all the pipes that are running in. This is the main dewatering column over here. This is a compressed air line here, and then behind here, there's a water line. And you can see the electrical cables that run in this particular location. So then my next slide, we're going to take a little bit of there's going to be a video that shows what it looks like underneath the cage as you're traveling up through the shaft. And in this, what we see right now is the conveyance, the cage running through the old steel sets, okay? See a lot of built up debris on them. And we're going to transition very shortly into where the new steel is. And now you can see, that transition zone. You can also notice a significant change in the vertical distance between those sets as well, too. That was a bearing set right there. You can see the pipes over on that one side over there. And then the cables are running right down this spot over here. So here's a time-lapse view of a station set that's constructed. So essentially, you can see the various steps that are involved. You have the work decks. This is the cage work deck here. This is the skip work deck here. And here's a steel piece that they bring the conveyances are used to bring all the various steel members down. Piece by piece, it all fits together. And it's as simple as that. So another task that we were faced with here was work associated with the head frame. The head frame was constructed a long time ago to a set of safety standards that needed to be updated. And so I'm just going to show this little clip here that kind of gives you a view of the head frame structure and some of the changes that we had to make to that. So this is is kind of a view of the head frame, the Ross head frame, that shows all the various structural members. And so we had to strengthen some of the members. And you can actually see here the members that are in blue that are right here. Those structural members were reinforced to be able to handle what we call a dogging load. And that's in the event of if the rope that hooks up to the conveyance would ever disengage, then the special a kind of a locking mechanism would just grab onto the guides and stop it right in its track. So that feature was not built into the original head frame design, and we've since built that in. So another important task for us here, at the bottom of the Ross shaft, at the 4850 level, we have a lot of excavation that has to be done. This isometric view, the image that you see that's in this orange brownish shade here is what the existing excavation looks like at the 4850 level, and the gray shaded area is going to have to be what the excavation outline is going to be as part of the work that's necessary to develop LBNF, okay? And you can see that in the figure beside here, because we have a whole bunch of pipes that have to come down the shaft, cryogen pipes, that are necessary to operate dune and bring the argon underground that's going to be in these large detectors. So you've got argon pipes, you've got nitrogen pipes that are coming down the shaft, and you see this large structure that's built to support the pipes as they come out of the shaft. And we also have to consider that there are going to be large components of the dune experiment that are going to have to be brought underground. And we've made some changes, to the cage conveyance that I'll show in another slide here to enable that to happen. Basically, those large pieces have to be swung out of the shaft, so we've got to make enough room for them to be able to be swung out of the shaft. Other work that we're doing, we've got major work that's being done on the hoist right now for the Ross shaft. This is a photograph that shows a hoist motor. All the hoist motors for the Ross shaft are going to be taken out and refurbished. We've got new brakes that are going to be put on all the hoist drums, and this is kind of an example of what a new hoist brake looks like. New clutches for both the production hoist and the service hoist as well too. There's a bunch of mechanical components, bearings and bushings on the various shafts. They're going to get sent out for refurbishment as well. This is what we call pinion brakes. So it's an added brake that goes on the coupling between the motor and the drum, just as an added safety feature. But what's most significant, I think, is the new drive system that we're going to be putting in. The current hoists are operated with the old mechanical systems, and we're going to build a new drive system in that's all computer controlled. So we're going to be bringing that up to the 21st century. Another main component of the Ross shaft is a new cage, and this basically shows the design of the new cage, which is actually just starting in fabrication right now. This cage has been especially designed to get the most possible space for bringing in large components to service, the LBNF /dune experiment. This view shows one of the features of the new cage is that you can bring these large structural beams underground, which are necessary to build the cryostats from which all the liquid argon is going to be, which is where all the liquid argon goes. These beams basically even stick above the height of the cage, and this distance here is about 12 feet. Just to let you know, these beams even sit higher than that. So we have, the roof. There's components of the roof that can be removed to enable these special components to be brought underground. And we've also got, a special deck that's also added that can be basically set on top of the cage so that the guys can do shaft maintenance as it becomes necessary. We've got new skips that have been built for hoisting the waste rock from underground, and that's basically what they look like. So after that, I thought, just a few fun facts about the Ross Shaft. Okay, what is this total depth? 5,132 feet, the height of over 3 Empire State Buildings, okay? The other thing is like 6 times the depth of the open cut. We all stand out, we can look out the window, and I can't see the bottom of the open cut. You need 6 open cuts to get to the bottom of the Ross Shaft. The total amount of steel that we put in the shaft, over 7 million pounds of steel has been put in. Top speed of the conveyance, over 30 miles an hour. And the time it takes for a tape measure to free fall from the top of the shaft to the bottom, 18 seconds if it doesn't strike anything on the way. You knew that was coming, didn't you? I know that from experience. Okay, Ross Shaft by the numbers. There's a lot of information there, and I'm kind of running out of time. If anybody's interested in knowing, essentially the speed of the conveyances are going to be running the 1,300 to 2,500 feet per minute range. The skips are going to have a capacity to hoist as much as 3,000 tons per day, for interest's sake, the total cage travel time. A one-way trip is basically with all the upgrades we're going to do is an 8.5-minute trip. Now it's a 15-minute trip, and so I'm really excited to see when we get everything done, just how much faster everything is going to be operated. So in conclusion, the Yates and the Ross Shafts were crucial to the success of the Homestake mine and are critical to the future of the Sanford Lab. And a refurbished Ross Shaft is going to be the workhorse for the development of LV&F and Dune. And the Yates Shaft is going to continue to support experiments at the Davis campus, including LZ and others to the future. What questions do you have? Yes, Tim?
You said you had to widen the Ross Shaft where it had shifted in. What's going to keep it from doing that again?
It's not. So what we did was we over-excavated to, we looked at how fast that encroachment was occurring, and we said, listen, we have to account for that in the future. So we over-excavated to allow for some movement to take place.
So it will?
It will.
Over decades?
Over decades. And the other thing, what's important to note too, was that there were periods of time during the mine operation where that convergence was happening faster than other times, and it has since slowed down, mostly for the reason is that the mining has stopped. Okay, a big reason why that convergence was taking place, not only because it was a highly stressed ground, but they were mining out the ore that was around the Ross Shaft, and all that did was accelerate the movement. Okay, now with the mining stopped, that has drastically slowed down. Okay. Yeah. Yeah. So no, actually, the manway is located within certain sections of the shaft, and it's essentially located to provide emergency egress from the pumping stations. There's a total of 4 pumping stations. The idea then is if somebody happens to be working at a pumping station, that they have the ability to egress from that pumping station to a level above or a level below that connects up with the Yates shaft, okay? And in the event, see the strategy for in the event that a conveyance gets stuck in the shaft, which is highly unlikely, the way that would work is that you would bring down if the cage gets stuck, you would bring down a skip, and which is going to have a platform on it, and you'd transfer people from the cage over to the skip. Yes.
Did they backfill around that Ross building?
There's a lot of open holes there. I think they did some backfilling, but Dave, do you know if they backfilled?
Oh, yeah. It was
Yeah?
sand filled.
Okay.
And what is the compressed air you talked about?
Yeah, so the compressed air, there's a 6-inch pipe in the shaft which provides compressed air for pneumatic equipment that could be operated at any one of the levels. It also provides a backup air system, air supply system for the refuge chamber, which is at the 4850 level. No, we have new compressors that have been installed in the Ross head.
How much time elapsed from the time you started to remove 3 old sets to the end of installing 18 feet of new sets?
Yeah, so that's a really good question. The first couple of sets that we did, it would take like a week, okay? And by the time, it's like anything else, after you do it enough times, you get really good at it. I've seen the guys do it as quickly as like 4 shifts, 2 days. They were working, 2 12-hour shifts, okay? So in 4 days, strip out the old steel, put in new ground support, install a new set, okay? Of course, that depended, if you were in the Ross Pill area, things got a lot slower there.
I gotta say that crew right there doesn't look any different than the crew was when I was there. Same crew.
Same crew, okay. Yes, sir?
So where are the compressors now? Because the compressors that used to be are gone. The
So-
old Ross compressor room is empty.
So there's, the requirement for compressed air far less than what it was back in the mining days. There's only like a 600 CFM compressor that's in the head frame right now. And so it provides, the air that the guys were using for those new, for putting in the bolts and for running the chipping hammers and any other miscellaneous small pneumatic equipment, okay? So I think there's talk about installing a second compressor in the head frame, but it wouldn't be anything more than another 600 CFM compressor, okay? Randy, did you have a question? No. Okay. Yes, sir.
So Sid, when they finished the Transcontinental Railway, they had a gold spike to put in. Do you have a gold bolt to put in here?
I think we should.
I think you should.
And there's one guy here that I'm nominating. This guy right here, Dan James. He's been on this job since the very start. I think he should be given that special.
I think you should put a gold bolt.
Yeah.
Where's the money coming from?
So the funding for the construction of the Ross shaft has come from a variety of sources. It started the initial funding came from the state of South Dakota, and then it transferred essentially from the Department of Energy. Yes.
I had always heard this, it might be a wives' tale, but the reason why the time limit had increased to 15 minutes was because some of the scientists or whatever were scared from the speed, so I wondered if you could clarify that, seeing as I saw that the goal was to get back to that 8.5 minutes.
Well, the scientists that I work with, they're all very brave people, and I've never heard them complain about that.
I was wondering if maybe you could clarify why it is 15 minutes now instead of 8.5, and what you're doing to get back to that speed.
So it's, a big part of it has to do with the condition of the hoists, okay? And I kind of touched on, the work that's being done there with improving, putting a new drive system in and putting in new brakes and that kind of thing. But essentially, before we put the new shaft steel in place, there was a number, like that Ross Pill area where you had the steel converged, the conveyances would get stuck there if you didn't run them through fast enough, okay? And I don't know if you saw the earlier slide that showed the condition of the steel with, the webbing with big holes in it. You could not safely operate conveyances at that speed. Yes.
Tell us a little bit more about the crew. How many people, do you get different skill sets, or is it a
different skill sets. You know, for a project that carries on for a period of 7 years, you're going to get there's going to be rollover with the crews. What I think is, you know, I mean, essentially, look at this guy here, Derek Becerro. Okay, Derek is a guy who's an engineering technician, and he started off, you know, working in the Ross shaft, and eventually transitioned to a guy who now supports science, you know, helping the guys who are building the LZ experiment. You know, some of these other guys, you know, they come from a mining background. Danny James is a guy that used to work in a homestake mine, loads of experience. Jerry Hinker in the background, he's also an experienced miner. And some guys, they're just new, young guys that were interested in doing this kind of work, local guys, okay? And, you know, you have a mix across there. So, yeah.
I saw in that CAD drawing that you brought up earlier,
Yeah.
there's some parts highlighted in red. What's special about those?
Man, I can't even remember any. Which, are you talking about the head frame?
Yeah. There was one, it was like a cross piece that was highlighted in red.
There's some of those that have to be reinforced, so that could have been.
Yeah, I don't remember seeing it. Maybe I'm getting colorblind or something like that. I just saw blue and black. But you know, there were. I know that in previous, you know, isometrics that I've seen, they were, you know, members that needed to be reinforced were identified as red. We should get 50 years out of it. It's always, anytime, you know, the life of a shaft is a function of the maintenance that you put into it. And, you know, that's one of the things that the slide that I showed with the new cage shows a maintenance deck on there. And as it's a routine part of your operation, you've got to plan on doing periodic maintenance. So, but with the new shaft steel that's been put in place, extremely strong steel, okay? 5-inch by 7-inch by half-inch hollow structural steel is just really, you know, compared to the old H-beams that were used there, hollow structural steel is just as strong as you can get. Yes?
Where's the steel coming from?
So the steel is coming from, Al, I should know the answer to this question here. I know that True North Steel is the fabricator. They got it from Chicago, Sugar Steel in Chicago. That's where they. Yes?
During the years between the closing of the mine and the opening of the research facility, was there any maintenance done on the shaft?
There was not.
Just all into disrepair?
It just, basically, they put a bulkhead at the collar, and that is it, okay, and allowed the facility to flood. So the water, you know, started, you know, the mine was opened down to the 8,000 level. By the time re-entry was established, the water had come up all the way to the 45, 50 level. So you had about 300 feet of the Ross shaft was underwater. Okay. So, yeah.
How long did that take to pump that up?
You know, I mean, pumping is going on as we speak here right now. But I want to say that it took at least a year to get down to the 48, 50 level. Yeah.
Could you talk a little bit more about, you said there was dogs?
Yes.
Is it box the cable?
It actually, no, these are, and if you actually go to the cage that's parked out in the visitor center right now, and if you look at the top of the roof, right where the guides, where the conveyance would run along the guides, you'll see a couple of teeth that are basically sitting there at an angle. And they're basically in that position, being held in place by springs. And if the springs come loose, they snap into place and dig into the timber guides, and that's what locks the conveyance. It just you know those teeth dig right into the cage, into the wood guides.
What was replaced, that you said, in the Ross shaft?
So in the Ross shaft, in the head frame, for whatever reason, the guides in the head frame were not strong enough to be able to support the load that would come if those teeth dug into the into the guides. So we had part of the work involved reinforcing all the steel in the head frame to support, a dogging event that would take place in the event,
To keep the head frame from collapsing.
No, it was not. It's not to keep the head frame from. Well, it would be in the event that a dogging event took place. Then what would happen is, yes, some of those members would have failed. That is correct. Yeah.
You're not still using wood for the cage and skip guides, are you?
We're using wood for the cage guides, but not for the skip guides. Yes.
If the conveyance were to fail,
Yes.
and the locks need to be engaged,
Yes.
does that require human intervention, or is that all just mechanical and it would immediately lock in as soon as the conveyance were reversed?
It requires no human intervention for that to happen. It's a simple mechanical device that when the load is applied, the teeth are spread out. If the load is released, those teeth spring into action.
You said you might want the slack rope system, describe that too.
Do you have a question? Al has a question about a system called the, excuse me. There is what we have, what is called a slack rope monitoring system. And what that does is it monitors, basically there are load cells in the head frame underneath the sheave wheels, which are resting on a base. So the slack rope system is a type of load monitoring system that basically monitors the total weight that is being applied to it as the conveyances are raised and lowered down the shaft. And if for whatever reason that load that's applied to those load cells is reduced, it triggers an action. It applies the brakes of the hoist. So it's an interim step between. It's a safety step that would occur before an actual dogging event would take place. Okay, so these are, like I said, this is a sensor that actually, the slack rope monitoring system was not in place when the homestake mine was being operated. So there really wasn't as much control to be able to determine whether or not the rope was slack. And the way the rope would be slack is if somehow the cage became disconnected from the rope, or if the conveyance got stuck in the shaft, then the rope would become slack as well too. So it's just an added safety feature. Yep.
Is the Yates shaft going to get a makeover like this?
You know what? The Yates shaft in its current form can't last for the next 50 years. Okay? And, not without a lot of maintenance. And it's like I was saying before, there is, of the amount of availability, there's only 40 hours a week, of which the Yates can be used for servicing the lab. The rest of the time is spent doing maintenance on it, which is, it's not the long-term solution. I think, when the Ross shaft is complete, it is going to be, heavily used, okay? And right now, it doesn't have that capability until it's completed. But as soon as it's in service, we've got to do the LB&F construction has to take place. And that is basically going to suck up all the amount of time that the Ross shaft can offer. So it's not like you can say, well, now the Ross shaft is done. Can it replace the Yates shaft? No, because we got to build this massive experiment down at the bottom of the Ross shaft, and that's going to suck up the time for the Ross shaft for at least the next seven or 8 years.
So can we do one more question? We're running out of time, but Syd, can you stick around for a little bit? If anybody else has a question, we'll take one more. I think right here, yeah, that's hand raised.
Okay, so if you have a dogging event, how much weight would that support if the cable should separate? Because if I understand this correctly, when burned, the two killed, were in the cage, the rope burned through, fell onto the cage and broke to the bottom of the shaft. So is it, I guess is it really an effective thing, or is it just makes you feel better?
So,
If I may, historical point, the Ellison shaft was a flat belt hoist, did not have a dogging system. It is because of that event that Yates and Ross, and they developed dogging safety systems.
right,
And that accident.
But
and
how much weight would it carry if, let's say the cage is at the
Yeah.
38,
So
and
that-
it burns through at the shaft head, that's a lot of weight.
so the dogging system is designed to handle 2.5 times the weight of the maximum payload, okay, of the cage and its full payload. Okay? So there is extra safety margin in there for, you know, that kind of load.
Okay. Thank you, Syd. Thank you for everybody coming. I'd like everybody to give themselves a big round of applause because our official counter over here said that this is our biggest audience ever. Sorry, David Vardaman. You'll have to do it again. Thanks again for coming. Everybody have a good night.
Have a good night.